Welcome to Millikan's oil drop experiment. This was the experiment that allowed us to calculate the charge on an electron. It was conducted in 1909 by two scientists, Robert Millikan and Harvey Fletcher. In 1923, Robert Millikan won the Nobel Prize for this experiment. Harvey Fletcher did not because he was a student at the time. Here is a photograph of the equipment that was used in the experiment, and here is a labelled diagram of that equipment. Here we can see a spray can, and what that does is it sprays oil droplets into the space at the top of this container. Oil was used because water would evaporate too quickly and you wouldn't be able to complete the experiment. Then X-rays were shone into the container to ionize the droplets of oil. Some of them became ionized because of the friction as they were sprayed into the container, but the X-rays were able to ionize the rest. At the bottom of the container is a space where there is an electric field, and any oil droplets that make their way through this gap will be exposed to the electric field. On this photograph, the gap would be roughly here, and here would be the space with the electric field, and you can see that here is a microscope looking into that space. Ionized particles might be positively charged or they might be negatively charged. A positively charged particle will be that way because it's had electrons stripped from its atoms. A negatively charged particle has had electrons added to its atoms, and there will be a mixture within this container. Any oil drops that make it through that gap will be exposed to the electric field. If it's a positively charged particle, then it will be attracted towards the bottom plate. If it's a negatively charged particle, then it will be attracted upwards. All of the oil drops have a weight. And if they have a negative charge, then they will be attracted upwards. The voltage across these plates can be carefully controlled, and the observer can look through the microscope and watch and change the voltage until the oil drops stop falling downward and remain stationary within the electric field. And what that means is that the two forces are balanced. The weight is the same as the upward force exerted by the electric field. And that force, of course, is proportional to the charge on the object and the voltage and the distance between. The experimenter is controlling the voltage, so we'll know what that value is. The experimental setup will have been carefully measured, and the distance between the plates is also a known value. We just need to calculate the charge. And we can do so once we've reached equilibrium in the space between the two plates, because when the two forces are balanced, they are equal. And we know that this is true. So if we know these two values and we know gravity, the only thing that we need to know now in order to calculate the charge is the mass. And we can do that using something called Stokes' law. Stokes' law is a mathematical expression for the force of drag, and it was developed by George Stokes in 1851. Remember that this experiment was being done almost 50 years later in 1909. George Stokes lived until 1903 and therefore was not around to see his law being used in this experiment. Stokes' law tells us that if we have an object and it is falling and it has a drag force on it and reaches terminal velocity, then the force for terminal velocity must be equal to 6 pi multiplied by the viscosity of the liquid multiplied by the radius of the sphere, and we are assuming that it is a spherical object for this law to be true, multiplied by the velocity of the object. We know many of these things. 6 and pi are just numbers. The viscosity of the fluid that it's travelling through, which is air, was known. The radius and the velocity were not. So the aim of the experiment was to select an oil droplet, observe it through the microscope, and alter the voltage across the plates until it was in equilibrium. Once it's in equilibrium, you can note down the voltage. When this was done, Millikan and Fletcher switched off the electric field and observed the oil droplet falling and reaching terminal velocity. They did this by looking through the microscope. They measured the velocity and calculated the radius. That allowed them to calculate the mass. I'm going to show you how they did some of those calculations now. So here we have a simulation of Millikan's oil drop experiment. And you can do this yourself. Here is the website. So we have our spray bottle, we have our container, and we have our microscope observing the space between the electric plates. We have a stopwatch which will help us in calculating the velocity of the oil drops as they fall. So let's begin. So we have oil drops in the upper part of the chamber, and in this circle here we can see the view through the microscope. Notice that they are all in this central portion because they fall through a very small hole, and so the oil droplets are appearing in a very controlled way through the microscope. So at the moment there is no electric field. I've not switched the voltage on, and you can see that the oil drops are falling under gravity. You should notice that they are all of them falling at a constant speed, because when an object has a very small mass, it reaches terminal velocity very quickly. What I'm going to do next is I'm going to turn on the X-ray to ionize the droplets in the container and turn it off. The oil droplets are still falling. I'm now going to turn on the electric field so that we can start adjusting the voltage to capture an oil droplet. We want it to be in equilibrium. So I can increase the voltage, and you'll see already that the oil droplets have slowed down. Some of them that have quite a large charge on them are already being attracted upwards. Let's see if we can select some and have them appear near the top. Okay, there's a good one. Okay, you can see that I've captured this oil drop here. We're going to ignore the others and just focus on this one near the 0 mark. So we know the voltage that's been applied, it's 1300 volts, and we also know the density of the oil because we know what type of oil is being used. I've got this captured droplet near the top here. I've got the voltage that's been applied in order to put it into the state of equilibrium. What I'm going to do next is I'm going to switch the voltage off, and I'm going to observe it as it falls downward through the viewfinder, and I'm going to measure the time that that takes. So I'm going to reset my stopwatch, and what I'm going to do is I'm going to switch off the voltage and then move over here and press start on the stopwatch once we get to the middle point, because I can't do both at the same time. So I'm going to pick a nice easy place to start the timer. Here we go. Start and stop. So it's gone half the way through the viewfinder. The full distance is 0.5 centimeters, so it's gone 0.25 centimeters in this time. So from this time and this distance, we can calculate the velocity, we have the voltage, and we have the density. So in the first part of the experiment, we knew that the force of the electric field was balancing the weight of the oil drop. And that told us that this was true. We had some of these variables, but we didn't have the mass. And we got the mass from the second part of the experiment, when the voltage was switched off and the oil droplet began to fall. It reached terminal velocity, and we were able to measure the distance and the time that it took to fall. And what this allowed us was use Stokes' law to say that the force of drag was equal to the force of weight. That is Stokes' law. We could now measure the velocity. We have the value of the viscosity of air, and the rest are just numbers. The only thing that we're missing is the radius. So what we can do is use some existing knowledge and a couple of mathematical tricks to calculate radius. We know that the mass of any object is equal to its density multiplied by its volume. The oil drops are spherical, so the volume of a sphere is 4 pi r cubed. What we can do now is substitute for mass this expression. We can cancel and rearrange and that allows us to calculate r. Now that we have the radius, we can use it in this equation to give us mass. Now that we have mass, we can use it in this equation to give us the charge. And that's what Millikan and Fletcher did hundreds and hundreds of times. They did it for many, many oil droplets. And what they noticed was that even though the oil droplets had different amounts of charge on them, some of them might have 5 electrons worth, some of them might have 20 electrons worth, they noticed that the numbers were all multiples of the same value. They noticed that the charge on all of the oil droplets was always some integer multiplied by 1.6 times 10 to the minus 19 coulombs. It was always a whole number. And that told them that the smallest amount of charge that can exist is this value here, which is the value of the charge on one electron. And that is how the charge of an electron was measured.